Hello, this is Professor Brown-Cedarberg, and we're going to be talking about multi-dimensional arrays. First, let's define multi-dimensional arrays. The classic definition is that they are arrays of arrays. And while that seems circular, it's actually a very good definition. Because multi-dimensional arrays are arrays in which each element of the array is itself an array. Now, there's no limit to the number of dimensions we can have in multi-dimensional arrays. Although humans typically have a difficult time visualizing anything beyond 3 dimensions. And a 3-dimensional array could be visualized as a cube. A 2-dimensional array, we can visualize that as a spreadsheet. In our lecture, we're going to be concentrating on 3 and 2-dimensional arrays. Now, when we're dealing with multi-dimensional arrays, just as with single-dimensional arrays, we have to declare and then create the arrays. We declare a multi-dimensional array this way. Here I'm declaring a 2-dimensional array. And it's 2-dimensional because I just have 2 pairs of square brackets. That's a 2-dimensional array. I say its type, the number of dimensions by the number of pairs of square brackets, and then the name of the array. And here we've got an array named myArray. So there I declare myArray. I then create the actual array, that is, put aside the storage space, and I do so with the keyword new, repeat the type, and then specify the size of the dimensions of my array. So here I've made my 2-dimensional array size by size, so it's squared. Same number of rows, same number of columns. The value that I pass in to establish the size of each one of the dimensions has to be a whole number. I can pass in a specific number, I can pass in a value stored in a space, I can pass in the result of a calculation or mathematical calculation, but it has to be a whole number. Having actually created the memory space, put it aside, I then assign that value to the namespace myArray. Remember, in myArray, that namespace goes the address of the first element of myArray. You might be wondering, if I have a more than 1-dimensional array, how do I find the first element? We'll talk about that in a little bit. So here I've declared and created a multi-dimensional array. In this example, a 2-dimensional array, and I did it with 2 lines. I can accomplish the same thing with 1 line, with the type, my open and close square brackets, the name of my array, the assignment operator, the keyword new, repeat the type, and then the specific sizes of the dimensions of my array. So here I declare, here I create, and here I assign. Now, there's no limit to the number of dimensions I can have in an array. A 5-dimensional array would be declared this way. I have the type, 5 pairs of square brackets, a name, the assignment operator, the keyword new, repeat the type, and then 5 numbers passed into the size of each one of those dimensions. Now, with a 2-dimensional array, I'll declare it this way. Simple 2-dimensional array that's size by size. That first size that's passed in is the first dimension. The second dimension. Java is a row-centric language. The first dimension is the number of rows. The second dimension is the number of columns in a 2-dimensional array. So a 2-dimensional array, first number passed in, first size is the number of rows, second is the number of columns. As I expand the number of dimensions, I remain row-centric. So if I have a 3-dimensional array, the first number passed is the number of rows. The second number passed is the number of rows in each row. The third number passed will be the number of columns. In each one of those rows, that's one of the rows. We'll talk more about that. Remember though, Java is a row-centric language. So, if I have this, a 2-dimensional array called myArray, it's going to hold characters, and it's 3 by 3. If I wanted to visualize that, I could do it this way. myArray, that namespace holds an address. The address points to the space where the information is held. So the first space of myArray holds the address that points to the first element in the first row. That's row 0. Remember, we index starting at 0. So in space 0 of myArray is an address. It points to the first element of the first row, row 0. In space 1 of my array is an address. It points to the first element in my second row, that's row 2. In space 2 of my array is an address. It points to the first element of the third row, which is row 2. So this is what memory looks like as we have a 3 by 3 multidimensional array. We can also visualize it this way. And we want to look at it this way because we want to be aware of how we index multidimensional arrays. Java is row-centric, so our coordinates for our positions, for our elements in multidimensional arrays, always start with a row. So here we see on the left-hand side the rows. They start row 0, 1, 2. At the top, the columns 0, 1, and 2. We see that what's in the upper left-hand corner, that's the first position. That's position 0, 0, row 0, column 0. Going across that row, we have from 0, 0 to 0, 1 to 0, 2. So our row number remains the same. Those are all the elements in the row. If I go from top to bottom, we'll see that I have the elements in each column. And you'll see that the coordinates, the first coordinate, the row number changes, but the column number remains the same. So I have 0, 0, 1, 0, 2, 0. Each position in my two-dimensional array has a unique identifier. Each position in any dimensional array has a unique identifier, and it's accomplished through this coordinate system. Remember, it's always row-centric. So in the upper left-hand corner, I've got 0, 0, my first element. In my lower right-hand corner, 2, 2, my last element. Now, as we're manipulating 2D arrays, we're going to use counter-controlled loops. We're going to use for each statements, though that enhanced for statement, and then a lot of nesting. Now, we could use while loops, but that doesn't seem most efficient. A counter-controlled loop allows us to be sure of how many times I go through a loop. A for each statement also allows me to be sure how many times I go through a loop. However, with a for each statement, that enhanced for loop, as I iterate through an array, I can only access the elements in the array. I can't change them. With a counter-controlled for loop, I can access and change the elements. We'll concentrate on counter-controlled loops here, and we'll have nesting as we use those counter-controlled loops. Now, as we manipulate our multiple dimensional arrays, we're going to traverse through them. As we work with them, we're going to use an instance variable, the instance variable length. And it's an instance variable of all arrays. The way I access it is the name of the array dot length. And what will be returned to me is an int that will tell me the number of elements, the number of items in that array. Every array has the instance variable length. We're going to use that as we control our loops, as we iterate through our loops and access the elements in our arrays. So here's a one-dimensional array. In a for loop, I iterate through each position, and I'm putting a value into each position. So I declare an int I, give it a value of 0. I say as long as I is less than the length of the array, as long as it's less than the value returned when I access the instance variable length. Every time I go through this loop, I'll plus I. And what I do in the loop is I just put into space I the value 0. And so I'll iterate through the entire array, and I'll put into each one of the spaces of that array the value 0. Now, if I'm going to work with a two-dimensional array, I'm going to do pretty much the same thing, but I'm going to nest. It's going to be a little different. So here's two for loops, the outer loop, inner loop. Notice the outer loop deals with the rows, the inner loop deals with the columns, and we're going to go through this in detail. My outer loop always starts with the rows, then I go into the columns. So as my outer loop executes, I'll do every element in that row, each one of the columns, and then go to the next row. I'll do every element in that row, then go to the next row. Now, I suggest that you use descriptive names. You'll note here that I didn't use the variable I used row and column. And notice that what we have as the control in the outer loop is the length attribute, the length instance variable of array name. Array name.length is going to tell me how many rows I have in that array. You'll note the inner loop is controlled by array name sub row dot length. That will tell me how many elements I have in that specific row. So array name dot length tells me how many rows in an array. Array name subrow dot length tells me how many elements in that specific row. This example iterates through a two-dimensional array and puts 0 into each one of the spaces. You'll see that in that inner loop with array name subrow column is equal to 0. All right. Now remember, the outer loop we're dealing with the rows, the inner loop the columns. So I'm going to create a 3 by 3 array and call it my array. So it'll hold ints. We can visualize it this way. Here's memory space. Each one of the positions in my array have coordinates. Upper left-hand corner, it's row 0, column 0. Lower right-hand corner, row 2, column 2. We're going to iterate through that, through two loops, an inner and outer loop, and we're going to place into each one of the spaces of my 3 by 3 array the value 0. So here's the inner and outer loops that will accomplish that. I declare in my outer loop an int r, give it a value of 0, and I'll say as long as r is less than myArray.length, the length of the array, I'll continue through iterating through the loop. As I iterate through the loop, I'll increase r. That's my outer loop. My inner loop, I declare a variable c, I give it a value of 0. As long as c is less than the length of the specific row that I'm in, I'll iterate through this inner loop. As I iterate through, I'll increase c. Inside this inner loop, I will put into the space rc the value 0. Now, let's trace some of the values. I'm going to trace the value of r, the value of c, the value of myArray.length, the value of myArray sub r.length. We know that the value of myArray.length is 3. This is a 3 by 3 array. There are 3 rows in it. I'm going to establish r, give it a value of 0, so r is 0. I'm going to test, is r less than myArray.length? Yes, it is. I go into my inner loop. I give c a value of 0. I test, is c less than myArray sub r.length? MyArray sub r.length is 3. That's the number of elements in row r, row 0. I therefore go into my loop and I put into the space myArray r0, that's 0, 0, the value 0. I increase c, c now has a value of 1. I test, is c less than myArray sub r.length? Yes, it is. Go into my loop. Put into position rc, the value 0. r is 0, c is 1. Into position 0, 1, I put the value 0. I increase c, c now has a value of 2. I test, is c less than myArray sub r.length? Yes, it is. I go into my loop and I put into position 0, 2, rc, the value 0. I increase c, c now has a value of 3. I test, is c less than myArray sub r.length? No, it is not. I go to my outer loop, I increase r. r now has a value of 1. I test, is r less than myArray.length, which we know is 3. It is. I go into my inner loop. In my inner loop, I establish c and give it a value of 0. I test, is c less than myArray sub r.length? That's 3. And yes, it is, so I go into my loop and I put into the space rc10 the value 0. I increase c, c now has a value of 1. I test, is c less than myArray sub r.length? Yes, it is. I put into position rc of my array, that's 1, 1, the value 0. I increase c, c now has a value of 1. I test, is c less than myArray sub r.length? Yes, it is. I put into my array rc, that's 1, 2, the value 0. I increase c, c now has a value of 1. I test, is c less than myArray sub r.length? No, it is not. I go to my outer loop, I increase r now has a value of 2. I test, is r less than myArray.length? Yes, it is. I go into my inner loop. C is given a value of 0. I test. I pass my test. I put into RC, that's 20, the value 0. I increase C. C now has a value of 1. I test, is C less than myArray sub R dot length? Yes, it is, because myArray sub R dot length is 3. I then put into the space myArray RC, the value 0. I increase C. I test. C is indeed less than myArray sub R dot length. I put into myArray RC, the value 0. I increase C. C now has a value of 3. I test. We fail that test. Failing that test, we increment R. R now has a value of 3. We test, is R less than myArray dot length? It is not. We're through. So having iterated through this entire multidimensional array, I've populated each element with its value of 0. And I populated each element because I used that length variable. And my length of my array here in the first line, that's 3. That's the number of rows. In the inner loop, myArray sub R dot length, that returned back the length of each row as I iterated through it. In our 3 by 3 array, the length of each row was indeed 3. This allowed us to iterate through, populate this two-dimensional array. The arrays that we've dealt with thus far have all been of equal length and width. Rows, they were square. Now let's look at ragged arrays. And a ragged array is always what we call ragged to the right as you look at it. It has irregular length multidimensional arrays. That's what it is. It has irregular length rows within a multidimensional array, or irregular elements. Let's look at a two-dimensional. Here's a ragged array. You see the first row has 7 elements, the next one has 6, the next one has 4. This is a ragged array, and as we visualize it, you can see that it's ragged to the right. So the first row, row number 0, has 7 elements. The next row has 6, the next row has 4, the next row has 6, the next one 7, the next one 2. They're ragged, that is, there are different number of elements in each one of the rows. And this is a two-dimensional ragged array, and that's as far as we'll get when we're looking at ragged arrays, just 2 dimensions. Now, how do I work with ragged arrays? Well, I'll declare it in this first line. I declared and created a ragged array in this first line. It's an array of ints, two-dimensional. I'll call it my ragged array, and I'm going to create it here with new int, but I'm passing only one value, 6. There'll be 6 rows in this ragged array, but I haven't established how big each row will be. I do that here in the next line. So I'm declaring and creating the ragged array in that first line, but only as to the number of rows. When I establish how many elements in each row, I'm doing that in these next 6 lines, where I say my ragged array sub 0, that is row 0, will consist of a new array that'll hold ints, and it'll be 7 elements long. My ragged array sub 1, that is the second row, will be a row of 6 ints. The next one 4 ints, the next one 6, the next one 7, the next one 2. So with these 6 lines, I'm actually creating those rows, the individual rows of my ragged array. And after I execute those lines, that's what I'll have. This ragged array, different lengths to each row. All right, so I'm declaring and creating. I declared my overall array, my number of rows with that new int 6, and then with the next 6 lines, each one of those specific rows. Now, if I want to populate a ragged array, I do it the same way I do a non-ragged, because I'm using that attribute length. And so the outer row, the outer loop, that my ragged array dot length, that'll be the number of rows. The inner loop, my ragged array sub R dot length, that'll tell me how many elements in each specific row. So I don't have to do anything different. I'm just populating this ragged array just as I did a non-ragged, because I'm using that length attribute. Now, here I'm just traversing and printing a ragged array, but I'm doing so using that length attribute, so I just go through it as I would a non-ragged, because that length attribute, that instance variable, will control how many elements I have, that I'm going to look at, so that I'll never have an array out of bounds issue. All right, so what have we looked at today? We've looked at multidimensional arrays, which are arrays of arrays. Each element of a multidimensional array is an array itself. There's no limit to the number of dimensions. We can